Hi everybody, my name is Jackson Burns. I'm a rising senior at the University of Delaware, working here at MIT with Dr. Connor Coley from the Chemical Engineering Department for the summer. And I'm going to briefly tell you about my work in leveraging machine learning and data mining in order to predict substrate reactivity in small molecules. So let's get started. Just a little bit of background to get us going here. Pharmaceuticals, particularly small molecules, are extremely ubiquitous in our modern economy. The third, fourth, and fifth highest earning pharmaceuticals are small molecules. As a matter of fact, Eliquis, Revlimid, and Imbruvica, meant to treat atrial fibrillation and cancers, respectively. Now, it's in our collective interest to try to produce these as quickly as possible, but if you were to go into the history of any of these three molecules, you would see decades and decades of publications being made just to try to get the synthesis of these down perfectly. Imbruvica, in particular, is interesting. The patent is valid until 2026, but as of 2016, almost 15 different routes had been patented just because this is such an interesting and important medicine. Now, the goal of this project, why don't we use machine learning in order to accelerate the process of drug discovery and optimization by creating a model that could predict yield automatically if we tell it which species we're trying to combine together. And to do that, we need to leverage the data that's already out there in the literature. So how we actually go about doing this is using the Chemical Abstract Service database, which is a proprietary database we've been granted access to thanks to CAS or CAS. We aggregate a group of chemical reactions. In this case, all of them involve the samarium iodide catalyst as a proof of concept for this greater procedure. We begin by aggregating these together, and then we go through the process of parameterizing them. So to do that, we use a lot of different molecular descriptors, both topological descriptors like fingerprints, which is essentially just a representation of where the atoms lie in space, and electronic parameters, which represent some of the more complex chemical descriptors, things like the amount of electron density that's over top of a particular atom. And in combination, we use those to describe the species. And here's what we saw over time. We evaluated a host of different machine learning approaches. So everything from neural networks to simple nearest neighbors algorithms to the very common random forest regression models. And the biggest trend that we saw was by implementing intelligently chosen quantum mechanics parameters, which are the electronic ones, which I mentioned before, we were able to achieve much higher performance than we were using sort of the easiest example of parameters. We started out with a root mean square error of about 33%, which relative to a lot of what's being published in literature right now is not very good. The standard is about 10 to 15%. That's our goal. And by making some intelligent decisions in terms of the parameterization approach, we were able to reduce that all the way to about 24%. So we're moving towards our eventual goal. The current best model right now implements these quantum mechanics parameters, but with the addition that we only include the parameters for the atoms which are precisely involved in the reaction. We found that over time this reduces the experimental noise as you add more and more examples. So some of the future directions we'd like to do for this project, we would like to continue this development, of course, to try to get it down to our goal root mean square error. Once that's done, we would absolutely like to distribute this model as trained for those interested in this particular type of chemistry. And then from there, we have some very interesting extensions which we're investigating as we speak, actually. We want to extend this to more diverse types of chemistries, and then using meta-learning, try to train a general model, which could answer essentially any chemical question just given the amount of data that we've trained it right now. And then if you were to connect that to a computer, it could potentially automate the exploration of chemical space on its own. If you'd like to hear more, if you have any questions, feel free to stop by my poster room or send me an email. And thank you for stopping by.